Okay, so today we're going to kind of complete the picture of what makes something a vector space, but we're not actually concerned with proving vector spaces in general. We have a long list of things that are vector spaces. And I remind people, I always refer to the big three. Okay? The ones we spend the most time on are things of this nature. These are sort of the big three. The first one is Rn. So for a specific value of n, R3, R5, R10, that's the set of all vectors of that dimension. That is a vector space. In fact, that's where the term vector space comes from, because they're vectors. This is the set of all matrices, m rows, n columns. It does not have to be square. Determinant has nothing to do. Inverse has nothing to do with vector space. Vector space has to do with things like closure and stuff. And then the last one would be the set of all polynomials of degree n or less. You would have specifics. These are the big three. You do not have to prove these are vector spaces. You can now rely on the assumption that yes, they are. What we actually spend most of our time on are not these guys. So if I said, let big V be a vector space. So big V is a set. It doesn't necessarily have to be pure vectors, but it's a vector space. Then let big W be contained in V, which means W is a subset of V. W could be all the way up to V. It could have one element. Okay? W is a subset of V. Our question is, how do I prove whether W is a vector space or not if it's a subset of a vector space? Okay? So here's the picture I want you to see. So here's V, and here's W within V. Okay? I already know V is a vector space. I'm not trying to prove that. I know V is closed to addition and closed to scalar multiplication. I know V contains the additive identity of that particular set. And the thing is, W, this is one of the things people waste time on. If something's a subset of a vector space, you can't fail any algebraic property. You can't fail commutativity. So a lot of times, one of the questions I ask you, hey, determine if this was a vector space or not. If it's not, show me all the things that fail. Hint, hint, it is impossible to fail any algebraic property if you're a subset of a vector space. You see, if I take two elements of W and add them in reverse order, it doesn't somehow fail that. I'm living inside a big vector space. Commutativity still holds. Distributive property still holds. Associative property still holds. All of these things still hold. The question is, if I grab any two elements in W, let's call that one U, and let's call that one V, and I'll use vector notation for this. Question is, where does U plus V live? Is U plus V, I'll write it like this, U plus V, is it in here, or is it out here? I know it's contained in the big circle. I don't know if it's in W or if it's outside of W. So I need to show that W is a vector space, but I only have to show three things. And I mentioned the three things last day. I have to show both closures and that the additive identity of the vector space is actually in W. Okay? You with me on that? Now, technically, could W be the empty set? Okay, I know you're in discrete. Has anyone completed discrete math? There's something, and this is completely tangential to this course, but this is something you may have learned in a lower level course. There's something called a power set. It's the set of every possible subset of a set of things. So let me take a really simple set of things. I have this set, you know, A, B, C. Well, I could have A, I could have B, I could have C, I could have A and B, I could have A and C, I could have B and C. Are there any left? Well, how about the whole thing? And then there's one more. This is every possible subset of my original set. So if I said, let's put all these into a big set, then we call that the power set. But it's important to know that there are these two guys. The whole set is a subset of itself, and the empty set is a subset. I'm not violating anything. And also the question is how many then? Well, you notice there's 1, 2, 3, 4, 5, 6, 7, 8. There were 3 elements. I wonder if there's any relationship there. Is it simply 2 to the number of elements? Yes. That's really, really important.
That makes sense.
The empty set is a proper subset of every set. So I have a vector space. Is it possible for W to be empty?
Yes.
Sure. And here's the crazy thing about the empty set. By the way, first of all, you can't fail any of the algebraic properties. We know that. So if I take nothing and I add it to nothing, I still have nothing. So I haven't violated, it's closed to addition. If I take nothing and I multiply by a scalar, I still have nothing. So it satisfies closure of scalar multiplication. I've now got 9 of the 10 axioms satisfied. So does that make it a vector space? No. Why? The empty set cannot contain the additive identity. So a vector space cannot be empty. And in the textbook, the author makes it very clear. You have to show your set is not empty by showing it has at least the additive identity. Now, let's suppose for a moment, just for fun, let's keep it simple. Let's suppose this is actually R3. Let's keep it simple. Is it possible that the whole set W has that as its only element? Again, a set can be empty. Let's suppose W has exactly that element. That's kind of a boring vector space, or I should say a boring set. Is W a vector space?
Yes.
Well, again, the other 7 are automatic. Okay, if I take the 0 vector and add it to itself, I'll get back the 0 vector. Okay, closure of addition. If I take the 0 vector and I multiply by any scalar, I'll get back the 0 vector. And it has the additive identity. Oh my goodness. This humongous set of one element is actually a vector space as long as the one element is the additive identity of the original vector space. So a vector space can have a finite number of elements. But what's interesting is a vector space either has an infinite number of elements or it has one. It can't have a second element because then I would fail both closures, wouldn't I? Just make up something other than the 0 vector, then any scalar multiple of that would not be in the set. That added to itself would not be in the set. Okay. So I can have something that trivial. So as long as it's not empty and it contains at least the additive identity of the vector space. So now, if I can show that W, now go back to our generic. I have a vector space V. W is a proper subset of V, meaning W is completely contained in V. There's no parts of W that aren't in V, in other words. If I can show that W is closed with respect to addition, closed with respect to scalar multiplication, and contains the additive identity of V. If I can show those 3 things, then the term we use is, remember, W is a subset of a known vector space, and I've just proved W itself is a vector space. So we say that W is a subspace of V. So the term subspace means you're a subset that is itself also a vector space. It sounds like a made-up word. It is. By the way, in my lunch today, do you know what I had? I had some plum cots. A couple of years ago, they called them pluots. I get them at Sprouts. Now they call them plum cots. It's a hybrid fruit made from, you'd never guess what 2 fruits they put together. Plums and apricots. They called them pluots a few years ago, and now they're called plum cots. I don't know why, and I asked the guy at the Hika, it depends who we're buying them from. Is that a made-up word? Absolutely. But anybody who's had one knows exactly what it is. I'm saying that facetiously because this is a made-up word. A subset that is a vector space. This is a subspace. Subspaces are where we spend most of our time trying to show things. I don't have to prove to you that R3 is a vector space. I have to prove that some subset of R3 that I'm working with is itself a vector space. Because if it is, then everything that vector spaces have as properties apply to the subspace. There's so many benefits from being a subspace. So we're gonna prove it. All right? Now we did a problem last day. So let's suppose I give you the following. The set D3 Okay, I'm defining a set. What do you suppose D3 actually means?
The diagonal 3 by 3 matrix.
Yeah, it's actually a real thing. So D3 would be the set of all 3 by 3 diagonal matrices. You know why I only put the 1, 3? We do one, when it's square, I usually only put 1. Just to make it easier to remember. I could put 3 comma 3, but it'd be redundant because it can't be a diagonal matrix unless it's square to begin with. So it's a set of all 3 by 3 diagonal matrices. Meaning I have zeros off the main diagonal. Now, can A, B, or C be 0?
Yeah.
Can any of them be? Yes. It's just that everything else has to be 0. I would like to prove that this is a subspace, or that it's not a subspace, but of what vector space? M33. Because this is the first thing I need to notice. D3 is contained in M33. Now, in this case, I do need 2 numbers. When I said diagonal matrix, a diagonal matrix and a triangular matrix are square. They have to be square. So that's why we sometimes only put 1 number, because there's no possible way of confusing it. But in general, a matrix doesn't have to be square. So I know this is true. So what I need to do is create a couple matrices and then do our algebra. The process algebraically is very simple. When I had linear algebra in college, we didn't have a lower division linear algebra. We only had an upper division. And so we started on proofs on the first day of class. Like we were doing this type of problem on the first day of class, and I remember I was blown away. I had no idea I was a calculus guy. I mean, calculus was like literally the easiest course I'd ever had in my life. You know, it wasn't even a challenge. And then all of a sudden I'm in this abstract proof-oriented class going, I have no idea what you're talking about. And man, did I struggle. Oh, that was a hard class for me at the time. I remember, partly because I didn't have a lower division version of it. And it was all proof from day one. And so as I learned what was going on, things started making more sense. And I had a great instructor, but he didn't really explain. He just said, let's prove this. I didn't know what went into a proof. I'd never had a mathematical course where we did proofs. Well, then every course after that was proof-oriented. So most people, their first upper division math course is usually the roughest one because it's the first one you've been exposed to proof. If the same course had been my 3rd or 4th course, probably would have been easy. So let's create 2 matrices. So how about we let capital A be, I'll do this, A1, 0, 0, 0, B1, 0, 0, 0, C1. And let's call capital B, how about A2, 0, 0, 0, B2, 0, 0, 0, C2. I've got 2 random diagonal matrices that I've just created. Okay? So now, first thing we're going to do, what is A plus B? It'd be A1 plus A2, and then here would be B1 plus B2, and then here would be C1 plus C2. Does that look right? Okay, I made up 2 random diagonal matrices, added them together, and I got that. Question. Is this contained in D3?
Yes. Yes. Yes.
Is it still diagonal, in other words? That's really the question. Is it still diagonal? Yes. Do this exactly as I'm showing you. This is not the time to get creative. People love being creative. No, there's times you can be creative on a proof, but not this. I'm showing you how to write it, and every single human being who does this should be saying exactly the same thing at the same place. You can't have closure unless you prove containment. And most of the time when people turn in answers, they don't bother with this statement. There's no conclusion I can make until I've shown the sum is in D3. The most important thing I could possibly say is that the sum is still in D3. Therefore, D3 is closed with respect to, I like using WRT because I'm lazy, with respect to addition. I've knocked the first one out of the way. I took two random elements of the set, added them together, and proved that the result is still in the set. That's what it means to be closed with respect to addition. Excuse me. Okay, now, next, scalar multiplication. Let's take k times a. Better new one than this. Take k times a. What is k times a? For any real number k, it would be ka1, 0, 0, 0, kb1, 0, 0, 0, kc1. Do you agree? Nothing clever going on here. When I multiplied a by a scalar, is it still a diagonal matrix? Is it still a 3 by 3 diagonal matrix? Yeah, I'm pretty much not going to lose the 3 by 3 part, I'm pretty sure. Okay? So can I say this is contained in D3? Yeah. Actually, you know what? I'm gonna change this slightly. We are taking two specific things. We're not taking two sets, so we really shouldn't be using containment. What symbol should we really be using? Anybody knows sets? Containment is, that's not a good symbol. Containment would be set. I'm actually showing I have one thing.
Oh, is it an element?
Element, good. This is better. This is better. It's more specific. I'm not taking a set of things. Although you could say, doesn't this represent infinitely many things? Yeah, but I'm taking two of them. I have infinitely many things, and I'm just grabbing two of them at random. So element is better. Element is better. Okay. D3 is a set. Sets aren't elements of sets. Sets are containing sets. Individual things are elements of sets. Okay? So, therefore what?
D3 is closed with respect to
Closed with respect to scalar multiplication. Okay? Again, the same idea. If I took any element in the set, multiplied it by any real number, the result is still in the set.
Oh, real. Never mind. You answered my question. You said K is real.
Yes. If k wasn't real, would I still fail? Or I mean, would it still? Sorry. Would it be possible to fail for different versions of k?
technically, if it was I,
And D3 specifies that the elements have to be real.
Yeah. So generally speaking, when we're dealing with real valued things, we have to be using real valued scalars. If I back up and I allow a, b, and c to be any complex numbers, then I would allow for complex coefficients. There's not going to be a situation where you're requiring real numbers and then allowing complexes. When we get to the complex part, we'll see that all restrictions will be removed, and it's actually easier to prove certain things. Because I can't lose anything. It's a little messier, the arithmetic, because we're not comfortable yet with complex numbers. But when we get there, it's not a big deal. It's way in the future. But I'm glad you asked. That's a great question. So what we're saying is k is a real valued scalar, because I'm only dealing with real numbers at the moment. Right? We're not going to somehow slip in an I or something. Now, I've just shown closure. That was really, really simple, wasn't it? I mean, I didn't have to do anything weird. I'm going to show you what a lot of the textbooks do that's correct, but probably overkill. But it's still correct. Now, I'm not done. Remember, the empty set also is closed in both these areas. So now what do I need to do is the third thing?
the additive identity.
I need the additive identity of M33. And I need to show that that's in here. A lot of times we kind of just make that assumption automatically. So if A1 equals B1 equals C1 equals 0, then this is in D3. Do you agree? We just said a moment ago that the A, B, and C can be any real numbers, including 0. There was no restriction on the A, B, and C. We saw last day when I put restrictions on the coefficients, that's where I can get in trouble. By putting restrictions. Without restrictions, I'm probably not going to get in trouble. So what have we just shown? Therefore, D3 contains the additive identity of M33. D3 does not have its own additive identity. D3 is a subset of M33, and the additive identity for all 3 by 3 matrices exists. We know it's the zero matrix, but that zero matrix is actually in D3. I've just satisfied the big 3 that I need to. I am now finished with the problem, but I need a conclusion. So what do you think my conclusion is? I'll use a different color. D3 is a subspace of M33. That's my conclusion. That's what I was trying to show. When something is a subspace, you're going to find that the algebra required to do it is actually really, really simple. If there are mistakes that we make, it's not that we get bad conclusions, is that we have incomplete results. We jump the gun. We try to go too fast. We say things like, A plus B is this. Okay, let me move on to the next thing. Well, why am I doing this? Oh, this is in D3. Got to say that. And because I took any 2 random elements and I showed their result, that sum was in there, then I can make the statement. I need both of these. This allows me to say this. Okay? And once I claim both closures, and then I showed the existence of the additive identity. You notice I used the term additive identity, not zero vector. A lot of linear algebra students get kind of careless and they'll just use zero vector for everything. No, use zero vector if it's actually vectors. But if I'm talking about matrices or polynomials or integrable functions or continuous functions, there's an infinite number of vector spaces that are not vectors. So don't use vector unless it's a vector. Just say additive identity. Now, in this state here, what the textbook will say, I like saying this. D3 contains the additive identity of M33. This is what the textbook will say. And is not empty. It contains the additive identity, therefore it's not empty. That's huge. I think it's redundant. I've just said it has at least the additive identity. I think it's redundant to now say, and by the way, it's not empty. Well, yeah, it has this. But in most textbooks, they want to see this. I don't need this. I'll usually put this in the key. You go, oh yeah, that's right, not empty was important. Now, gotta be really careful. Let's just suppose that A2, B2, and C2, let's just suppose they were all ones. All right, then the identity matrix is in D3. Do you agree? The identity matrix is in D3, so D3 is not empty. But I need to show it's not empty by showing it has the additive identity. Because I can take something that's not a subspace and it's still going to be not empty. It's having the additive identity is what I need to show. Not some random element, but specifically the additive identity. So these are the big 3. This is not complicated. There's no way this is ever complicated. So tell me how I can change the original statement of the problem. Excuse me. Tell me one thing I could change that would make this not a vector space, or not a subspace of M33.
Change one of the variables to a non-zero constant.
Okay, so take away one of those. So A and B, or A, B, and C are real numbers, but A is not 0. Okay, I like that one. A not 0. Why? Because now I'm going to fail. All right, I'm going to fail having the additive identity. Am I going to fail closure? No. No, it's not the closures. It's still going to be diagonal. If I took anything where B and C can be anything including 0, A can be anything that just can't be 0, and I add it, it's still going to be diagonal. If I multiply it by K, it's still going to be diagonal. No. 9 of the 10 axioms will still be satisfied, but I won't have the additive identity if I made one of those a non-zero.
But isn't it going to fail the 2 closures for like specific cases? If
Well, right now, this is a diagonal. I'll rename it, but if I said anything of this form, where A, B, and C can be anything, but A cannot be zero.
even with 5 and -5, those two matrices are going to produce a 0, so that's not.
Can I come up with a situation where, yes. And we did that with the polynomial, didn't we? Now, give me something else that would cause it to fail. I think something more obvious. Remember I said we're going to change this so it's not the set of diagonal matrices. What if I changed any one of those zeros to non-zero? And you put a specific number there, then when you add them together, you'll have a different number. You multiply by a scalar, you'll have a different number. Zeros are okay as placeholders. Zeros will never be an issue. It's non-zero values as placeholders that are the issue. Now, in my original statement, you go, but A, B, and C are not zero. Actually, they could be zero. These guys are required to be zero. It's the ones where you see a zero, if I put a non-zero number, that's going to fail. Okay, so I said there's a couple of things that a lot of the textbooks do that are correct. And here's where they do it right here. I'm going to erase this for a moment. They'll say at this point in the problem, they'll say, let A equal A1 plus A2, B equal B1 plus B2, and C equal C1 plus C2. Then what is the result of this? Then it's this. And the reason a lot of people like this is exactly the form. I mean, I can't mess this one up, can I? So they'll rename. Then over here, what will we do? Let KA1 be A, let KB1 be B, KC1 be C, and then I get the same thing. A lot of folks like doing that. I would never discourage you from doing that. I just think it's not necessary in this case because obviously this is a diagonal matrix. Renaming these isn't going to make it easier to identify that. Now, there are times when renaming them actually is a very good idea. I'm going to do that example next. Okay? Any question on this before we move on? I'm going to do one now with vectors. This will look like something we did last day. In fact, it's exactly what we did last day, but I want to, now that we have a little more insight. All right, so W, keep this simple. W is any vector of the form 3s plus 2t, comma, s minus 4t, comma, 2s. The last statement means there are no restrictions. There is an infinite number of possible vectors. Now, before I do anything else, where does W live? What vector space does W live in? That's really important that I identify that.
R3.
You mentioned.
How do you know?
So vector with 3 elements.
Because I have 2 commas. I mean, literally, that's how you know. Oh, I got thing, comma, thing, comma, thing. It's R3. I want it to be that obvious. I want that to be an absolute oh duh. And I will actually have people make a mistake on this. It's in R3 because I have 1, 2, 3 elements in my vector. Now, since S and T can be any real numbers, there's an infinite number of vectors here. Now, over the course of the next several weeks, we're going to keep coming back to this problem right here, and we're going to be seeing there's more information. There's, on the other side of this board, this is one of these, like, what do they call them, two-way mirrors or something. On the other side of the board, you can clearly see in here, but you can't see what's over there. There's a universe on the other side of this board that this thing is describing. There is so much information in this statement that we haven't discovered yet. We're going to be able to do things, take it apart, talk about dimensions, talk about all sorts of crazy things. Every time we learn something new, we're going to go back to here and go, oh, now I can also say this, now I can also say this. We're going to say, well, in Calc 3, do we deal with things like this? Yes, all the time. Okay? If I wanted to give you a physical, geometric interpretation of what this is, anyone want to guess what this is? In 3D, this is a plane going through the origin. It is a plane. This describes a plane, but there's infinitely many vectors, and all of them live on the same plane. Now, we don't know that yet. We will discover that over the next couple weeks. It's kind of cool. I'm giving you a very specific plane, and it is passing through the origin. How do I know it's passing through the origin? Because if S and T are 0, won't the 0 vector be one of the vectors? Now, that's how I know it's passing through the origin. Oh, but isn't it you know, to describe a plane, don't I need two distinct vectors? Yeah, there are two distinct vectors in that statement. You just don't see them yet. You're going to see them really soon, like a couple lectures from now. There are two very specific vectors in there. They don't have any S's or T's in them. I'll give you a hint, they're linear combinations. And so in that statement, there's a ton of information that we will glean over the next several weeks, and we're going to be able to do all sorts of crazy things. If that's a plane in 3 dimensions, then there must be a vector orthogonal to that plane. So if there's a couple of vectors hidden in that statement, then there must be a third vector, the one that's orthogonal, and now I can describe all of R3 starting with that thing. I can generate every vector in R3 starting with just a plane. There's so much things we can do. It's crazy. I can start with one vector in R3 and eventually generate all of R3 if I do, you know, the right things at the right time. It's crazy. It's out of control. All right, I want to prove this is a vector space. So let's describe two vectors. Now, that's a capital W. I'm going to make up two vectors, and I'm going to call them little w's. So W1 will be 3s1 plus 2t1, s1 minus 4t1, and then 2s1. Let's describe W2 as 3s2 plus 2t2, s2 minus 4t2, and 2s2, where t1, t2, s1, and s2 represent any real numbers. But you notice it's got to be the same s2 all the way through. Okay, s2 can be any real number, but it's the same number all the way through. All right, here's two random vectors in W. So very specifically, W1, W2 are elements of big W. So make sure we understand. I'm trying to prove W itself is a vector space. But because it's a subset of a known vector space, I only have to prove three things. The two closures and the existence of an additive identity. That's all I have to do. That's all you ever have to do. Which is nice, because it's never going to be complicated. So let's start by adding two of these together. So W1 plus W2, what does that look like? Well, it's kind of messy at first. So it's 3s1 plus 2t1 plus 3s2 plus 2t2, comma, s1 minus 4t1 plus s2 minus 4t2, comma, 2s1 plus 2s2. Yeah, I'm just using the definition of vector addition. I'm not doing anything clever. Now, I really would like to say this is an element of W. Does that look anything like my definition of W?
Not yet.
Good. Not yet. Not yet. But if I perform a little bit of algebra, I might be able to manipulate it. Like namely, put things together, maybe factor. So how can I do that? Let's take this here. Can I write this as 3 times s1 plus s2 plus 2 times t1 plus t2? Can I do that?
Yes.
This is the key to making this work. Plus, or excuse me, comma, s1 plus s2 minus 4 times t1 plus t2, and then finally 2 times s1 plus s2. It looks a heck of a lot more, but it's still kind of busy. This is the reason why this is actually a really good idea. You don't have to, but this is a really good idea. I'm going to let s equal s1 plus s2 and t equal t1 plus t2. Because if I do that, then what will this be? 3s plus 2t, comma, s minus 4t, comma, 2s. It's just easier to see now, isn't it? I could have left it in this form. I have 3 times a variable plus 2 times a variable, and now I have the original variable minus 4 times the other variable. I didn't change anything, but it's a little harder to read this. But that clearly is an element of W. This is why this is actually a really good idea at this stage to do that. Did I need to do it for the diagonal matrices? No, it was really easy to read. They're still diagonal. There was nothing weird going on, but this is, let's face it, this is really busy. And you can't say this is in W because this doesn't look anything like W. What if I made a mistake? What if I have a wrong coefficient? What if I have a wrong sign? Yeah. I'll discover when I start manipulating. Therefore, W, big W, not the vectors. Vectors are not closed. The set is closed with respect to addition. Be very specific because you have addition and you have scalar multiplication, and those proofs look very different. All right, so now let's take any real number k and pick one of those. I'll use W1. So what is k times W1? Well, then that would be k times 3s1 plus 2t1. And then k times s1 minus 4t1. And then k times 2s1. Agreed? Great. And again, that doesn't look like, I mean, W doesn't have coefficients at k, that's coefficients of 2s and 3s and 4s. So can I manipulate this? How about if I rewrite it like this? 3 ks1 plus 2 kt1. Would that work for the first one? So I just used commutativity and associativity, rearrange and regroup. And this one, how about if I wrote it as ks1 minus 4 times kt1. And then the last one I wrote as 2 times ks1. So once again, if I say, let S be ks1 and let t be kt1, then this will become 3s plus 2t, s minus 4t, 2s. Again, this is where it's very wise, making that substitution. Because now it's obvious. I mean, it's exactly the form of vectors in W. So with absolute certainty, I can say this is an element of W. Therefore, W is closed with respect to scalar multiplication. Now, as a rule of thumb, if you fail one closure, you're probably failing the other. Maybe I could come up with an example, but I don't think I can. Where you could fail one and pass the other, it's pretty much a package deal. And if you fail the closures, it would be really unusual if you still had the additive identity. That just, you know. So it usually is all three or none of the three is really how it typically works. So the last thing I need to do, I'm not done yet. I've shown scalar multiplication and addition closed. But remember, the empty set would have satisfied both of those also. So now I need to show the existence of the additive identity. So go back to here, this is the last thing. If S equals T equals 0, then what can I say? If S and T are 0, then I actually have the 0 vector. And that's an element of W. A common error that people will do is they will actually state all the way through the problem that R3 is closed to addition. Now I've shown R3 is closed to scalar multiplication. Now I've shown R3 has the additive identity of R3. Yeah, I knew that ahead of time. That's not what I'm trying to show. I'm trying to show W has all of these things. See, W could fail to be a subspace, but R3 is not going to fail anything. R3 is a vector space. So what can I say now? Therefore, W contains the additive identity, you could say the 0 vector in this case, the additive identity to T of R3, not something else. Have we shown everything we need to show? So, W is a subspace of R3. That's the last thing I need to say. I'm now done. QED. Okay, I'm finished with the proof when I made that statement. Everything I said was true, but I'm not done because that was what I was trying to show. Because the only other conclusion I would make is W is not a subspace. At what point can I say that?
Any of those fail?
Good. Generally speaking, as soon as something fails, I'm done. So you go after whichever one is most obvious to you at the time. It's good form to be able to show all of them, by the way, just because it's good practice. we will not be spending a lot of time proving things aren't. We spend most of our time proving things are, because in a very short time, I'm going to do a problem of this nature, and you're going to say, oh yeah, that's a vector space. I already know it because I know what's involved in proving it. Right now, we got to go through the nitty-gritty of proving it. We got to roll up our sleeves, right? Get our hands dirty, do the whole proof. So then, over time, I can look at something and know if that's a vector space. I don't even have to think about it. It's just automatic. Okay. Now, I do want to spend a moment talking about certain things. On the quiz, I asked a certain question. I asked about additive identities. This should always be easy. But in general, I want to make sure you understand how to identify an additive identity. So if I said, for example, let's consider P3. P3 is the following set. It's the set of all things, A0 plus A1x plus A2x squared plus A3x cubed, where A0, A1, A2, A3 are real numbers. No restrictions. Any of them can be 0. Agreed? Any of them can be 0. So here's the thing. I would like to know the additive identity of P3. The best way to say this one is actually as follows. The additive identity is 0 plus 0x plus 0x squared plus 0x cubed. But isn't that just equal to the number 0? Yes, it is. But you're going to find over time when we're doing all sorts of analysis, we talk about things like dimension and all these other things, that if I write it in this form, it doesn't change my answer any. But there's certain things that I will see that I may not see if I just put the number 0. Do we all agree that equals 0? That's not even a question. And here's why that's so important from another standpoint. All right? I would like the additive identity of R4. Get out your calculators. This is going to take a while, right? Or maybe not.
The vector 0, 0, 0, 0.
That's it. I don't have to prove anything. That's the additive identity of R4. Okay. Let's do one more. The additive identity of M22. So what is M22? It's the set of all 2 by 2 matrices. So I want the additive identity. Yeah. Oh. I can take any 2 by 2 matrix and convert it to a polynomial of degree 3 or less. I can take any polynomial of degree 3 or less and convert it to a vector in R4. Because those 3 vector spaces are isomorphic. They're exactly the same form. They don't look the same, but they're the same form. How do you know they're the same form? Tell me something that's common in these 3 statements.
They all have 4 elements.
They all have 4, more specifically, they all have 4 zeros. Ooh, yeah, they have 4 elements, they have 4 zeros. So I can mix and match and rearrange. This is down the road. We're going to do stuff a little bit later on. But the whole idea is, if I didn't write this in this form, there's no way in the world you would say that this had anything to do with these guys. Because you just see the number 0. But by writing in that form, you say, oh, I have 4 places I can put zeros. There's 4 places I can put zeros. There's some sameness to these. There's something about these forms that's the same. ISO means same. Morphic means form. That's the whole point. That's why I say that's the most important word, but it's not the word that's important. It's understanding the concept. We're going to get to it down the road.
So M33 would be isomorphic with R9.
Exactly.
Seems like this gets messy really quickly.
No, because all you needed was the number. That was really all that mattered, was that you had the right number of things. And where they go, yeah, it depends on the vector space itself. This is all new unexplored territory. I don't expect anybody to say, oh yeah, I've got this. This is a piece of cake. But to go through the process, I'm not asking you to prove this is a vector space. We're starting with the assumption this is a vector space. It's already been done by people, much smarter than us, that, in a much higher pay scale kind of, right? But now if I take a subset of something, I need to show that's a vector space by showing it only passes 3 properties because all of the algebraic properties are inherent because it's a subset of the vector space. You can't lose any algebraic property. A subset of a vector space cannot somehow not be commutative with respect to addition, because then the vector space itself wouldn't be. That's why I say a lot of the times we're going through all of this stuff, and in the textbook the author will go through every single one of them. It's not really necessary. It's just the big 3. Okay? Any question on this? It's not hard to do, but we want to get it because the language, most of the time we're not working with vector spaces, we're working with subspaces, most of the time. But we can also be working with a vector space. If I'm working with a vector space, there's certain things that we discuss, dimension being one of them. We're going to start talking about this next time. But if I have a subspace, remember I talked a moment ago about something being a plane in 3D? Think geometrically for a moment. 3D is 3-dimensional. Tell me about the plane. Geometrically speaking, it's 2-dimensional. How about a line in 3 space? It's 1-dimensional. How about if I only have the 0 vector in 3D? It's actually 0-dimensional because it's only a point. So if I understand a little bit about the geometric part of it, it sometimes makes it easy to describe, but here's the tricky thing. I can use the word dimension in every case, but only in this one do we really think geometric. These are physical things, right? They're vectors. This is 4-dimensional. I can't really think in 4 dimensions, but I know this is 4-dimensional from a geometric standpoint. But guess what? So is this. Guess what? So is this. But we don't think about it in terms of the geometry. Now I go back to the calculus argument. When I talk about dimension in calculus, dimension is just the number of variables. Okay, so in the xy plane in baby algebra and even calc 1 and 2, right, y is a function of x, you're 2-dimensional. You have 1 independent, 1 dependent. Then you get to calc 3 and you learn how to have, right, any point on the xy plane can now be my input and my output will be the z. Now I'm 3-dimensional. Why? I have 3 variables, 2 independent, 1 dependent. What if I have a company and I make 10 things? My profit is a function of those 10 independent variables. So therefore, my profit is 11-dimensional. But where we get messed up is we think we have to be able to draw a picture. No, dimension in that case just refers to the number of variables, the number of independent plus the 1 dependent. That doesn't get weird unless I'm trying to think graphically. So in our case here, dimension isn't a graphic thing. When I have things that are pure vectors, it's much easier to talk about the geometry because there is geometry. If I'm in R3, I already understand the geometry. But dimension is independent of the geometry. Dimension just refers to, you said, how many things, how many elements. That's what the dimension is. Oh, that's why these are isomorphic, because they'll have the same number of things. It has everything to do with dimension, not geometry, but just the number of things. Okay? So I'm going to leave it at that because our brains are going to start swelling soon because the algebra of what we're doing is trivial. But like a lot of things, it's what the heck did I just say, right? I can do the algebra, but when I'm making a conclusion, what the heck am I saying? And that will come. This is very abstract mathematics that we're doing right now, not from an algebraic standpoint. That's easy. It's again, what are we saying? So we're going to walk away from this. The next couple of things we're doing is actually far more abstract than what we're doing today that we're going to get to next week. But again, not from an algebra standpoint. From a building block standpoint, we are setting the stage for every conclusion you will make mathematically for a long time in many, many other classes too, proof-oriented classes. This is very foundational. Some of the language that we are going to learn in this class does cross over to other classes. In discrete math, there are a lot of words that we use in both classes, different contexts, but the word doesn't change its meaning. There are certain words, though, it's painful because the same word in a different context means something completely different, and I don't like that. In a differential equations class, we can have a system of homogeneous equations. What does homogeneous have to do with?
It equals 0.
Yeah, things are equal to 0. Just keep it loose. Homogeneous has to do with equaling 0. So we on our first quiz, you solved the system of homogeneous equations. We love those because they're always going to be consistent. But in differential equations, you'll be working with a system of homogeneous equations, and then you'll be working with homogeneous functions, which has absolutely nothing to do with 0. In fact, it doesn't have anything to do with anything that you've ever used the term homogeneous for, but you might be doing those at the same time. Homogeneous functions and homogeneous equations, completely different meaning of the word homogeneous. Right? I wasn't there when the World Math Council decided we're going to call this. No, bad idea to use the same word to mean something else. But do we do that in math sometimes? Occasionally, yeah, we'll use something. But the words that we're using in this class in general are the same in every class. Different context, but the same. And I'll give you an example. In baby algebra, you guys remember when you first were learning functions? Do you remember one-to-one functions? That's a function that's always going uphill or always going downhill. It's called monotonic. We also called it one-to-one. And that meant the inverse was also going to be a function. Oh, now one thing you may or may not remember is that if I'm using up the entire domain and I'm getting the entire range of values, think y, think of a line, think of a cubic. Don't think of a parabola. That would be a bad one. But we'd say if I'm basically using everything in that range, we call it onto. How many have heard the term onto? Anybody ever heard that? Because that goes with functions. You'll do that in discrete math. One-to-one and onto go hand in hand. You can't have one without the other in the discussion. But in baby algebra, we typically limit it to the one-to-one. But those two terms go together from a baby algebra graphing a picture standpoint. And then we use those in this class to mean high-level abstract things, but they still mean the same thing. Okay, the term one-to-one still has that same kind of meaning, and onto, and so on. So there's a lot of vocab that is consistent with things you've learned before, you just haven't used it in the context. And most of that's going to come up in chapter 6. Okay? All right, let's go ahead and stop. Let me click. I'm going to bring up the